Hello everyone, my name is Matthew Lazaric and I'm here from the University of New Mexico to talk to you today a little bit about my research. So, first things first, introduction and motivation. One thing I hadn't thought a lot about in undergrad was that our nuclear data is inherently wrong. I'd throw a simulation into MCMP and believe that what came out, barring user error, was the capital T truth. But in reality, these cross-sections are built up from experiments with biases, errors, and uncertainties, and so these will always be tied back into our data. Evaluators, then, are given the job of taking these thousands upon thousands of experiments and coming up with usable data, or what we would call an evaluation. And so we wanted to find a way to make that process easier. Well, that process, evaluation, is a much more qualitative process than I think is usually assumed. Now, I'm not an evaluator, so I'm sure I'm oversimplifying a lot. But evaluators use tools that compare simulation results against experimental ones, and then they look for patterns. Let's say they run a suite of test cases and all of the thermal metal plutonium simulations consistently overestimate the value for K. This might indicate that the fission cross-section for plutonium might be too high, or alternatively that the absorption cross-section might be too low, or any combination that might result in a higher multiplicity. So the evaluator might finagle some piece of data and find that now the simulations match reality much better. What we want to do is we want to provide a tool that evaluators can use to help with this finagling. On the right here, you can see an example of that process that I described. A suite of 55 test cases are run, and you can see that they calculate the calculated to experimental ratio for each case. This ratio tells us how accurately our simulations match up with reality. And you can see here that some cases consistently differ from a C over E of 1, which would be ideal. Now I'm going to switch gears a little bit here to give a bit of a background about cross-sections, because if you're like me, when you've thought about cross-sections, your mind usually pictures something like this on the right, a nice line across 11 orders of magnitude with no issues whatsoever. As it turns out, these continuous energy cross-sections are built up from resonance parameters like you see here on the left. These resonance parameters include things like the energy of the resonance, that's the leftmost column, or the width of the resonance. And through mathematical trickery, we can represent all cross-section behavior as a series of resonances. Okay, and now I want to take a second here, because we know that resonances impact cross-sections. We also know evaluators adjust cross-sections to fit reality. And so the question we then asked ourselves is, can we use our knowledge of resonance parameters to increase the accuracy of our nuclear data evaluations? The overall goal of this work is to increase the fidelity of nuclear data evaluations. This aligns with the NNSA mission, as increased cross-section fidelity translates directly to an increase in the fidelity of our simulation results. This will help further our ability to detect fissile material. And so we set off to see what was possible. We needed to somehow express how resonance parameters impact continuous energy cross-sections. Well, to me, that sounds like sensitivity information. Perhaps we could use that to dial in the values to more closely reflect reality. Now, what do I mean by sensitivity info? Well, sensitivity information describes how a fractional change in a response R is induced by some change in the system parameters, gamma. Here the response could be the K effective of the system or the generation of some nuclide. What we want to do is use the information to dial in the correct values for a given evaluation. This term here on the right, the del sigma del gamma, is of real interest here because this is what's telling us the behavior of the cross-section as we dial in our resonance parameters. Now, with the traditional method of generating cross-sections, this term is hard to come by. However, there's a new-ish nuclear data formalism called the pole representation, developed by Richard Huang in the 80s, and it represents cross-sections as a sum of poles and residues. A special attribute of this formalism is that it can analytically Doppler broaden cross-sections on the fly, and as a byproduct, we are able to analytically determine our derivative term. Well, great. Now we have a way of generating that sensitivity info, only one issue. the pole representation is only implemented into OpenNC, and so I started looking into how I could implement some version of this into MCMP. To tell you more about this process, I need to jump back to the nuclear data side of things for a bit to give a bit more context. Okay, time for a nuclear data crash course. So the majority of our nuclear data comes to us through the lens of R matrix theory. R matrix theory can be thought of as a series of assumptions about nuclear reactions that let us essentially standardize our view of them. These assumptions include things like only two bodies can interact, a sharp cutoff point between Coulomb and the other nuclear forces, among others. From R matrix, we parameterize, choosing which parameters we want to use to interact with our framework, R matrix. The dominant parameterization is called the Wigner-Eisenbutt parameters, and they are those parameters we saw earlier and include things like resonance energies and resonance widths. This parameterization defines how we interact with R matrix theory, giving an idea of what dials we can play with. Once we have a framework, R matrix, and we know how to interact with this framework through the use of our parameters, we start to apply a set of simplifications, what is often called a formalism, so we can then build up our cross-sections. Unfortunately for us, well, me, it isn't possible to directly use these parameters for windowed multipole. This is because windowed multipole uses a different set of parameters, a set of parameters that isn't in NDEF, and so I had to go about finding a way of translating between these two sets of parameters. And so, the goal of this work was to implement a method of translating between these parameters. And as it turns out, the process of translating between parameterizations is rather tricky. In the original Huang paper, where he lays out the foundation for the multipole formalism, he also describes a method of translating between these parameterizations. However, this method came with some issues that weren't caught at the time. For example, it calculated the wrong number of poles, and this caused numerical instability and resulted in the root finding algorithm finding a cluster of poles around the origin. And so recently, a PhD student named Pablo de Cruz developed a rigorous method of translating between the standard Wigner-Eisenbutt parameters and the multipole parameters. Okay, so with all that, how do we actually go about translating between the different parameterizations? Well, the first realization came from Huang's paper, where he represented the transmission probabilities, and therefore the cross-sections, as a sum of poles and residues. But poles of what, you might ask? So at the heart of our matrix theory is a matrix called the transmission matrix. This matrix tells us how likely it is to go from one channel to another, where here channel just means a set of incoming or outgoing particles and their properties. Say a thermal neutron and a uranium atom going into a reaction, and it would be an incoming channel, and then a fission event would be an outgoing channel. This matrix U is often expressed in terms of another matrix called the level matrix A. This level matrix ends up being key to the process of translating between the standard parameterization and the one needed from windowed multipole. Now, I've been doing my best not to throw equations at you all, but here I think I have to. So, at the heart of finding those poles and residues is what's called a radioactive states problem. And if you've never heard of that before, don't worry, you're in good company. But in the simplest terms, it's in the form of a generalized eigenvalue problem. And so what we need to do is find the energy value here, epsilon sub j, that gives us a singular matrix, i.e. the matrix has a determinant of 0. Once we have that, the residues of this are the null space of A evaluated at that pole, and then these poles are then normalized. With our poles and residues, we can then generate our transmission probabilities. Now, if the A matrix is something straightforward with an easy relationship with energy, this isn't too bad. The issue arises when we look at how we define A. You can see that the energy relationship in this equation isn't exactly clear, the result of which being it is difficult to back out these poles. Now, this is where some of the formalisms I mentioned before come back into play. Formalisms were originally developed as the R matrix is theoretically infinite in size, as the number of exit channels for a given reaction is infinite, and so formalisms were introduced to simplify the method of generating our cross-sections. As it turns out, these formalisms also make solving the radioactive states problem a lot easier. For the most part, two major formalisms are used in the low energy range, these being multi-level Brett-Wigner and the Rich-Moore formalism. And as it turns out, when converting between these parametrizations, only the definition of the level matrix makes a difference. So, for example, the multi-level Brett-Wigner formalism defines its level matrix as the diagonal components of the full A matrix. And so, if we want to find the values that make this matrix singular, we just need to find an energy value that makes any one of the diagonal elements 0. What this then reduces down to is solving a series of polynomials in root E space. This is where the original Huang paper had issues, as the number of poles was overestimated. We must need only find the roots of the quadratic equation that lies in each diagonal element, and this can be done using Newton-Raphson. Once we have these poles, we can generate the residues by finding the null space of that level matrix, and then we're golden. We can generate our cross-sections and produce our sensitivities for the required evaluations. So as far as expected impact, once this work is successful, not only will we have produced the discussed sensitivities, but it will also generate more interest in the pole representation of the cross-sections, which has its applications in GPU Monte Carlo. Through MTV, this work has helped introduce me to new topics and connections that will be valuable as I work towards my degree. Hopefully this coming summer, I will work to continue this work at Los Alamos National Laboratory. As far as technology transitions, this work may increase interest in the on-the-fly Doppler broadening capability of windowed multipole, as well as its applications in GPU Monte Carlo. And so, in conclusion, this work may increase the fidelity of nuclear data evaluations and thus our simulation results, as well as increase the interest / feasibility of GPU-based Monte Carlo methods. And as for steps forward, I want to be able to generate these poles and residues regardless of the nuclear data formalism used, and so produce sensitivity for all possible nuclides and energy ranges. And so finally, I'd like to thank the Consortia for monitoring technology and verification for their support in this research.